All right, so this week we are going to be looking at human factors and human performance improvement tools. So these will be specific tasks or functions that we can do to evaluate or test certain conditions. So, first, I always like to discuss causation. When we say X caused Y, what are we actually saying? And that seems like a silly question, but a lot of times we take it for granted, our own perceptions of the flow of events and those kind of things. So, especially when you're looking at human performance investigations, you really want to have a very good understanding of the chain of events and how certain things caused other things. And then what does that mean when we start applying that to humans? Because cause is often confused with blame or accountability in the real world, which isn't always appropriate or accurate. Also, we'll run into this, again, taking advantage of taking for granted, I should say, the our notions of causation. A lot of times that'll get kind of binned up with common sense. And it's important to note common sense is not a real thing. There is no fundamental knowledge or competency or intelligence or anything of humanity. We're all shaped by experiences. We all learn in the same way, but within different contexts and environments, which changes what our own common sense is. And when we look at causation, especially if you go back to previous instances of human error and the belief of how humans perform, we get to a lot of focus on the worker and less on the organization, and especially instances where machines are never at fault. And that largely stems from the construct of agency, right? It feels weird to attribute a cause to a machine that has no agency and couldn't decide. But it's also important to separate cause from intention and agency and all that. We won't get too deep into this, but it's one of those things I like to bring up just so it's on your mind and you're not taking for granted the causal chain of events that make sense to you and that you're actually tearing those things apart. So this leads to systems causation. So we want to consider that everything serves some role in a system. What are the characteristics of systems? They are variable and have many different factors. There's a lot of interdependency of components or correlation of different performances within them. And your causal factors can be present in many different places and can be contextual, adaptive, or dynamic. Typically, when we're looking at human performance investigation, we are looking at how the system performed and what the human did to trigger some fault or error or mistake within the system. But it's important to have a good conception of that entire system before we start to evaluate all of the human performance role, because humans are the most dynamic of most systems in that we can adapt and kind of step into many different components. Okay. So when we look at what's our role from a human performance perspective, relative to system causation, we should be focused on fixing the system, not blaming what occurred. This is one of the biggest potholes you can step in when you're doing human performance investigation is you're focused too much on the why and the blame and the hand wringing of, oh, how'd we get here kind of thing, where our task is really to look forward and to create an instance where this event could not have happened again. So, as the investigator, you have to untangle the situation and find the root cause or causes, and then you'll develop corrective actions, which should serve to repair the system flaws and help design a solution which will prevent another occurrence. And we'll get into this a little bit more further in another lecture, but when you think about a root cause, when you hear that term, the difference between a root cause and other types of causes is a root was absolutely necessary for the event to occur, which also conversely means without the root cause, the event could not have occurred. Doesn't mean an event couldn't have occurred, but the specific one we are looking at could not have happened without that root cause. So that's an important thing to keep in your mind as you're starting to develop kind of these thought patterns and ways of approaching things, is you're looking for the one that would have made it impossible to occur separately. So when you're looking at possible solutions and those kind of things, that's what you have to ask yourself is, does this remove the root cause? So some definitions really quick. Root cause, we just talked about it. Fundamental causal factor, which, if corrected, will prevent reoccurrence. Causal factor. So this is a factor that shaped the outcome of the situation. One of the vaguest definitions I've ever seen of anything. Causal factor, you can basically chalk it up to, it's not a root cause, but it definitely is a problem or contributed or shaped things in some way. Extent of condition. So this is something we'll get into when we get further into kind of some investigation methods. But extent of condition can be a task or a concept. It's the extent to which the condition exists in other systems, processes, or tasks. So this is, okay, we have this condition that led to this event. Does this condition exist elsewhere? Great example. Let's say you have kind of a catwalk or scaffold type thing and the railing is loose. And you figure out, well, why was the railing loose? Oh, because maintenance has been short-staffed for the last year and has been focused on these critical system tasks instead of these little things. That's a great example of one where, considering the condition, maintenance being stretched too thin and their focus being on more system critical aspects, that means they probably haven't repaired or maintained any of the railings anywhere. So one of the tasks you would undertake for this, or corrective actions you would identify, would be somebody should go around and figure out if all these railings are loose. It's funny to talk about railings because now looking at barriers, right? Where this is a control specifically. Can be a physical barrier, I suppose, but for this we want to consider it as some physical or administrative control designed to promote consistent performance and defend against inappropriate actions. And it also, when we say physical, that also you might hear the term engineered control is also another term that you'll get thrown around that can generally be considered interchangeable with physical, just depends on your context. Corrective actions. These are measures that you take to correct the issue, whatever that may be. And there can be many of them. And we will get into, in a later lecture, we'll get into what makes a good corrective action. And then we had extent of condition, so now extent of cause. This is, instead of focused on a condition, so the condition of, in our previous example, maintenance being overstretched, what is the cause? So this is when we find the root cause. So if we go back to our maintenance being overstretched, okay, well, the cause of that could be they are having a hard time recruiting new employees. Maybe their management stinks and nobody wants to work there. Maybe there's not enough funding. Those are all potential cause threads that you would pull to eventually try to get to whichever one was the root. Then you look at, does that root cause have the potential to be present elsewhere? So let's say it's a situation where oh, yes, the management culture in this department really stinks, so nobody wants to work there and they're having mass exodus of staff. Okay, we figured out that cause. Does that kind of a cause exist elsewhere in our organization that maybe we need to attend to? Are there other groups that are losing people at maybe a greater than normal rate and could use some training or some changes in that space? So those are some just important definitions to just kind of keep in mind as we go through. And when we talk about barriers, I'm going to bring back this from the human error presentation about the Swiss cheese model applied to respiratory virus defense. So, barriers are slices of cheese in this instance. Each barrier will have imperfections. Each barrier can be overcome, can be defeated, all those things. That's why we have multiples. So the hope is, right, with what's the, if you consider joint probability, right, the likelihood of one barrier getting overcome is some number. The likelihood of that one and the next one is a smaller number, just by mathematics. So when we look at that, adding barriers can be a very effective way to minimize likelihood of error or risk. However, it's important to balance, right? You put too many barriers up and nobody can do anything. So it's definitely one of those that requires some nuance and attention in its design and implementation. So then when you look at HPI, so human performance improvement, there are specific tools, and this list can be incredibly varied. The list I have here is not exhaustive. Depending on the organization or the kind of school of thought, you can have many different HPI tools. And these HPI tools are typically things that you try to bake into a culture, a way of doing things, or just your personnel within training, like as you train them up to make sure that they use these type of mechanisms in their daily job. So some examples, we have self-check. So, instilling people with an awareness of their actions and an ability to be reflective in the moment. Very difficult. Check for understanding. This could be, this is a very critical one for management or supervisors, anybody directing work. When you give somebody a task, to ensure they perceive what you said the way you did. This can be a huge source of human performance issues in general. Somebody says go do X, and that person heard to go do that, but the way in which they did that maybe didn't match the mental model of the person giving instruction, led to an error. So it's important to do that check for understanding and have that back and forth. Peer check. So again, instilling into your workers awareness and reflection, not about themselves this time, but of others, and that they feel not emboldened or enabled, but they feel comfortable raising concerns with their colleagues, that they're not trying to get somebody in trouble or be pedantic or obnoxious. They're just trying to ensure everybody is safe. And so if they see something strange, they're willing to check their coworker and just make sure everything's good. That feeds also into a questioning attitude. This is also something that is kind of a something you have to imbue into your employees, but also is a cultural, like whole organizational concept, or it won't work, where everything gets questioned at every time. Nobody is above reproach. No decisions are above questioning, and those kind of things. Now, a lot of times, organizations will see this as a negative because they are looking at, they'll see it as you're not being positive, you're not being a team player, those kind of things. But really, what in the context that we're focused on in this course, right, is safety and accidents and events. And at that point, your power of positive thinking isn't going to help, but a questioning attitude can. So it's just an important thing to keep in mind. Then we look at procedure use and adherence. So this can apply to your domain. Maybe it doesn't. Depends on the work discipline, right, that we're looking at. Some jobs have very strict procedures that you follow. And then the HPI tool, right, is that you did follow the procedure. So that's the use and adherence of it. So that's one of those things, right, to be aware of when you start an investigation. Okay, what did they do? Okay, that was wrong. Why? And was there something that told them the right way? Was there a procedure? Was there instructions? Something like that. Then we have stop when unsure. This is another organizational thing of you're empowering your employees to stop everything in a task if they've got discomfort with what's going on. And this, this will sometimes run up against deficiencies or, oh, but we got to get this done because of deadlines. But again, it's in a safety incident, a lot of safety cases, a lot of accidents are usually because somebody rushed or we had to get this done and there wasn't enough questioning about the process, and then lo and behold, all the other barriers lined up and you had an event. So, and like I said, this list could be significantly larger as well. It really just depends on your application space. All right. So I'm not going to read all of these, but this is just the general investigation process per OSHA. And this will be important specifically for your domain to get a sense for how investigations are supposed to go. We just talked about procedures. There should be some kind of steps in the right way to do this investigation. So the way a detective with the police department performs an investigation is different than what OSHA does, which will be different from what, let's say, the IRS does if they're doing financial investigations. There's a lot of different angles to it, and it's important to be aware of where your organization and context falls within that. Are you bound by OSHA or let's say your transportation, so you're bound by the NTSB? Or is it that there isn't necessarily a prescribed process from whatever your broader domain or standard is, but your organization might have a process or a procedure that they have defined that this is how they want these to go into. So yeah, go ahead and pause this so you can read through these and kind of get a sense of what these steps are and what that means, and try to think about, if you consider any event that you've looked at, okay, what does this look like in that event? You don't have to map it out explicitly, but what would you expect to see? Because that'll be an important step. And this is a little bit of a simpler process. So typically, I'm going to focus on this figure on the right first. You have some immediate action that occurred after the event. So somebody took some step, they put something in a safe condition, they moved the thing, whatever it is. You then plan the investigation, collect your data, analyze the data. That should lead you to corrective actions and solutions. Then you write up the report. And on the left here, right, we have instances that fit into all of these as well. Secure accident scene, document the accident scene. So that's, the CSI little numbers next to things where you take pictures, those kind of steps. This is also where you'll conduct interviews. You then develop your sequence of events, conduct any cause analysis that you need to do. There are apparent and root cause analysis methodologies. There's some others out there too. So again, be aware of your domain. You'll then determine solutions. That's our corrective actions. Communicate it. That's our reporting. So, okay. So different application spaces. I've said that a few times now. So refer to whatever entity has jurisdiction over what you are focused on, or what your domain is. Adhere to those processes that are relevant for the situation and application space the accident occurred in. The goal, regardless of the system or incident or context, is to find the cause of the situation, not the blame. And these are just some really great causal statements that I love, that are just kind of odd framing. Nothing against newspapers, there's limited space on the sheet, and they've got they only have so many inches. So I always love it when I see funny headlines and things like that. So this first one, the county is going to pay $250,000 for advertising. The lack of funds that they have, right? That's a funny instance. And then obviously, fish need water, the feds say. You don't say. And that's funny. Those are just interesting ones to look at, right? And the way those are framed, probably not the reality of it, right? But the way those are framed is always interesting, if we're looking at it from a causation perspective, right? Okay, these are odd, so let's keep pulling the thread. But they're just also really funny. Okay, so resilience versus fragility. Okay, so what does resilience mean? So typically, the definition of resilience is that it's the characteristic of a system or component or process, etc., person, to maintain performance given faults or different events that are limiting their performance. So this could be, how well does the system cope with unreliable power, or if this component fails, and those kind of things. How resilient is it? How well does it perform in the face of adversity? So when we look at fragility, that'd be the opposite of resilience. So some somewhat recent examples, right? The Texas grid events that have happened over the last 5 to 10 years or so, where sometimes it's too cold for the grid, sometimes it's too hot for the grid. And it seems like there's definitely some fragile areas there that they need to work to, again, make more resilient. And similarly, in California, they had rolling blackouts. I remember this was a big deal a few years back, where it was being used as a fire prevention measure, because the utilities in California had done such a poor job maintaining their electrical infrastructure that there was a risk that, as that electrical infrastructure may fail or throw sparks or whatever in the middle of a dry summer, we get massive fires. And then if you look at like nuclear power on the far other side of it, right? Nuclear power, incredibly not fragile. As a general rule, nuclear power tends to be one of the safest industries on the planet. But one thing the reason I bring this up is some people will then say, well, yeah, but nuclear power is incredibly regulated and inefficient, which is very true. But inefficiency is often a symptom of resilience. If we go back to resilience, what is that system that can survive components going down and those things? Well, how does it do that? Typically does that through redundancies, through additional personnel. We can think of how that works. And a system with a lot of redundant components or excess staff, those kind of things, would also be considered inefficient. They're not maximizing their efficiency. So there's a little bit of a trade-off there. And then the final question, right? Are all accidents a sign of some kind of fragility? And that's one of those that we'll have to see as we go through, but often it's present there somewhere. There's some aspect that was fragile that maybe slipped through the cracks or was more fragile than people expected for whatever reason. But it's an important thing to consider. Okay, so we've talked a little bit about this in previous lectures, but sources of human error. So we have cognitive sources, memory, attention, vigilance, decision making issues, ergonomics. So this could be physical limitations that caused human error. I'll get back to these plane levers in just a moment. Psychosocial sources, so teaming, communication, some of those aspects, and organizational management structure. Recall if we go back to the resident pathogen analogy in the human error sections, the higher up in a hierarchy somebody is, the more pathogens they spread by default. So the more error conditions they propagate, just as a feature of their level in the hierarchy. Okay, so going back to these plane levers. So this is an old human factors origin story. So in World War II was kind of the birth of human factors as a discipline. And whether apocryphal or not, one of the initial stories was that they were training new pilots for the war effort, and they had the problem where this particular group of pilots in this plane kept crashing their planes. On landing, they would not drop their landing gear properly and drop their flaps, which would make the plane descend faster. And nobody could figure out what was going on. They trained people to pull the right lever, etc. But in the moment, these pilots were really unsuccessful. Come to find out, the levers were underneath the seat, so they were not visible, and they were the same. One happened to control the wings, one happened to control the landing gear. But in the moment, they were easy to mix up. So the solution, and this was an ergonomic solution, was to make them different shapes. So the landing gear here is a square, the wings are a circle. Then we have even some more realistic ones, right, where the landing gear lever is a landing gear or the flap lever is a flap. And what that helped people was they could start to associate these levers are different. One's a square, one's a circle. So that helps reinforce which one is which, especially where they can't see it. They can't see any labels. And lo and behold, people stopped wrecking their planes. So human biases and heuristics, we talked a little bit about these, but we'll go through them just a bit more, especially as we're doing human performance investigation. You want to be extremely aware of these biases and heuristics, not just in yourself, but also in the people you're interviewing. All right, so first looking at satisficing. Remember, this is the way most people make decisions. They pick the best available, which usually ends up being first best available, not the optimal solution. You've got recognition heuristics. Recognized alternatives are more valuable. I've done this thing before, so I'm more likely to select it as a strategy. Availability. Similarly, quick retrieval of an option makes it more valuable. So if we go back to what we discussed about memory and encoding and repetition, this plays with the recognition heuristic a little bit too, because for something to qualify as the availability heuristic, that just means it was the thing your brain gave you first as a solution. But the way our memory works, frequency of memory recall increases its likelihood of recall. So that's one of those interesting ones, right? It's not necessarily a problem that the option came up first. And that's an important thing to dig into, because maybe that option is right. And that's why it came up first, because in this context, it is the correct path. But then, okay, so if that was the correct path, then we know it wasn't a memory fault or that somebody was in the wrong rule state or something. Now we can dig into implementation or execution and see if there's an issue there. Representativeness. So this is a common problem. If X is similar to Y, then it's in the same category as Y. This will be a huge problem when you start to get into causal reasoning. People will start to attribute causes from systems that they consider similar, even though they are not the same system. You'll see a lot of that. Anchoring and adjustment. Arbitrary numbers, if we anchor somebody somewhere on a type of value or number, they will be less likely to deviate from that. And there's more if you're interested, looking up the Judgment Under Uncertainty paper by Tversky and Kahneman, or Daniel Kahneman's book, Thinking Fast and Slow, covers these, and also includes a reprint of that famous paper. So what humans are good and bad at. Now, before we get into this, I want to just state there is no way to train yourself to not be this way. It does not matter what training implementation, what your background is. It doesn't matter if you were trained in the military or you're just naturally a type A personality that's very organized and all of those things. This has nothing to do, and when I say good and bad at, that's not a subjective view. It's not a normative view. It's not saying you are good and bad at this in like a normative sense of right or wrong. It's just the reality. We are all humans. Our brains are very different, but our cognition tends to work the same, no matter what. And so these are important things to be aware of. No matter what, these are things people can't do well. So again, if we set up a situation or a process where they have to do one of these things, that's not a recipe for success typically. All right, so first, we are intuitive grammarians, but not intuitive statisticians. So this is true. We are not great at numbers. Even mathematicians and statisticians, just inherently, we don't have a good or valid perception of numbers and statistics. So, the famous study, again, by Daniel Kahneman and Amos Tversky, where they, it's similar to the Linda study that we discussed, where even trained, graduate level statisticians made poor choices on statistical problems. And that's not because they suddenly forgot statistics. That's because our brains don't fundamentally work that way. That's not the way we've evolved. You also have what's called the Dunning-Kruger effect. You'll hear this tossed around a lot, especially in like political arguments and stuff. But what it means is that we're bad at self-judgment. We overestimate how good we are. We underestimate how bad we are at whatever it is. And so this is a big one. People tend to think they understand things at a much higher level than they actually do. So that's another one to be aware of. Future consequences, or what we might call, simulating events into the future. We're not good at that. We tend to discount negatives, overestimate positives. We'll discount or consider the likelihood that we make a mistake or that some negative thing occurs. That's way less likely. It's probably going to work out well. Vigilance. So continual attention is one of the single most difficult and taxing things for a human brain. And this came from one of the fathers of psychology, William James, that noticed that forcing people to maintain continual attention on a task or a process was incredibly taxing on their cognitive resources. So we're not good at that. So if you've set up a situation where people are supposed to be vigilant, they're going to fail more often than not. And then repeated precision. We're not great at that. Even you take the best typist, and if you measured down to like a micrometer scale, where do they hit the key? They will hit the key everywhere, not in any one single place. That's because we are not precise at that level. We are precise within some range. So if you're having a task that does require repeated precision in kind of a granular sense, then you're, again, setting people up to fail. All right, and now we're going to go into some human factors stuff. So human factors is, in my view, human performance would be considered a subset of human factors. Human factors is an incredibly broad discipline and kind of can include many other disciplines and be applied in nearly anywhere humans are present. Human performance tends to be a slightly sub-focus within it, but which isn't to say it's less than. It's just if you need a disciplinary hierarchy, that's kind of how that would look. So I think it's valuable to discuss how human factors people get to some of these points in case any of these are valuable for your purposes. So first, we're going to look at task analysis. Then we'll look at functional requirements analysis and function allocation. HSI design, which we might save for a future lecture. Operating experience review, important human actions, and verification and validation. These are all steps that we do when we're designing systems or trying to ascertain some of those things. When we go through this, also to give them less weird names, task analysis is relatively straightforward. Functional requirements analysis, function allocation, this is really what's the human going to do, what's the machine going to do. HSI design, this would also fall into a user experience type domain, if you've heard that term before. Operating experience review, this is our user research. This is when we interview people. When we say operating experience review, we're saying review how this thing is done normally. Important human actions also can be called critical tasks, critical steps, those kind of things. These are the important steps you have to take to achieve success. And finally, verification and validation. How do we know the system is doing what it's supposed to be when it's supposed to be doing it? Same with people. So why do we do a task analysis? The question fundamentally is, did we set up the task and the user for success? Task analysis is a systematic process to evaluate how we're going to do this. What does success look like? How will we know if we had success or failure? And what factors can influence performance? Pros and cons of task analysis. So there are times to use it and times to not. So when should you use it? When task construction is critical to success and you're not sure where the error points are. It's used to break a task into subtasks, and it identifies what should have happened. And it's used to identify typically deficiencies in training, procedures, or procedure adherence. Now, advantages of task analysis: it will deeply familiarize yourself with the task. It does help to identify where the problems occurred while performing the task. And it can inform many different mitigations or corrective actions. Because as we break the task down into more granular pieces, we get a lot more detailed information about how that task was performed, but also how it should have been performed. Okay, now pros and cons of task analysis. So limitations. It can be very time consuming to do a task analysis. And that, depending on the budget or what your situation is, you may not have the time to do it. Then you have walkthrough task analysis is far and away one of the most effective ones, but it only is effective if it can be formed with the personnel that are normally responsible for the task, which might be difficult. Can be difficult to complete without firsthand experience. You typically will need SMEs from the system or process to kind of help guide you if you're an outsider, you're not aware of how that task should work. And it's also very easy to lose the forest for the trees. So we remember system causation. When you're focused very closely on granular task components, you can sometimes forget how that task fits into the overall system or organizational structure. Okay, so steps in task analysis. You're going to define the scope, so which tasks, conditions, procedures. Collect the data. This will usually be observational data, can be interviews, talk-throughs, walkthroughs. You might even have physical measures, performance data. You then have to interpret the collected data. So do you lay it out in a hierarchy, a list, a table? And you then identify your failure or error points. So where did the task performance deviate from the task as it was defined? Okay, and there's a few different main types of task analysis, but there's a lot of different ways to do this. So when we talk about interpreting collected data, how do you represent that information, which then informs how do you conceptualize the task in general? That determination will typically lead you to specific methods of task analysis. So you could look at hierarchical task analysis. That's one method. A tabular task analysis, a totally different one. Link analysis. Applied cognitive task analysis. Sometimes you'll hear cognitive work analysis thrown in there. There's a lot of different ways to do a task analysis. So if you're undertaking a task analysis, make sure you're using one that is best suited for your application, because these do have different pros and cons within themselves, and there's different schools of thought on which ones are best. Hierarchical task analysis. So this is a top-down method. You begin with the goal and then break it down into subtasks to achieve the goal. How deep you go can vary. It's not typically great when you have communication issues or extra task issues. So this would be different issues that maybe surround the task. They're contextual, different things. They're harder to catch in a hierarchical. Tabular task analysis. This is more of a bottom-up method. You begin with a subtask or a basic action, and you then build it up. It tends to get incredibly detailed, but it will capture cognitive steps in decision making very well. And it'll also capture task support and communication steps, but can be very time consuming. Link analysis. So this is an intermediary method. It lives between the tasks. So you're focused on the links between the tasks. So how a task may progress between phases, let's say, even if they're not strictly defined. It provides information on communication steps, captures interactions between processes and systems. And it's useful for teaming situations or complex handoffs or reliance on another group or another system or process. And then applied cognitive task analysis. So captures the specific cognitive demands of a task. So you're going to capture the information needs, what the demands are, why is that a challenge, what error traps are present, how could things go wrong, and cognitive support. So are there decision aids? Are there instruction sheets? Those kind of things. That's where this is really useful. Okay, so function allocation and functional requirements analysis. That heading there is a little bit misleading. Functional requirements analysis, you decide what needs to be done. Function allocation, decide who is doing it between humans or automation or the system components, different things there. Okay, so there's key FRA processes. This is also currently being updated, at least in the nuclear field. But there's an EPRI document that guides a lot of these. So it identifies functions that must be performed to satisfy the operational goals and objectives. It may overlap with probabilistic risk assessment or human reliability analysis. Those methods will often use decision trees or fault trees that, again, break down the steps needed for success. Not necessarily synonymous with important human actions or critical tasks, but can be, depends on how you're breaking it down. Some key considerations here: you need to determine the objectives of the task, performance requirements, constraints of the design. You need to define activities that must be accomplished to meet the objectives. So those are our critical tasks, right? And define relationships between functions and plant processes that are responsible for performing the function or executing the broader goal. And then function allocation is where we look into, is automation essential? So maybe manual performance of this task raises health or safety concerns. Maybe it has to be performed incredibly rapidly. Think about your ABS system in your car and how much faster it can pump your brakes than we physically can. Or the function requires precision beyond human capabilities. The function requires human reliability greater than is available. This is where you could deploy an HRA analysis to better determine the human error likelihood or probability. And when it's not possible to automate, but any of these are conditions may be present in some level, then you typically want to increase staffing or build safety systems that can reduce the likelihood of single point failures. So typically you want to automate, right? The fundamental takeaway: if functions may feature high human error rates and high consequences for errors, look back to what are humans good at? What are we not good at? And then, is automation desirable? Maybe the function is complex and just easier for computers to perform. Maybe it requires many repetitive actions that can be fatiguing or boring. Maybe it has high cognitive workload, long periods of boredom that maybe would span like a vigilance problem. Maybe it creates high levels of physical workload or fatigue, so this is where your ergonomic considerations come in. Or it interferes with the performance of another manual function. So automate if, while humans may perform these tasks, they do not do them well, may be error prone, even if they are not of serious consequence. Then we look at, is human involvement essential? Involvement. The function is a core human responsibility. So this could be communicating to other workers. Maybe automatic response is difficult. It's challenging to model this instance in the control logic. Or you might have an accountability question where personnel need to remain in the loop. They need to be able to take over control. Maybe human involvement is required for other tasks. Or it's a deliberate task to maintain operator vigilance or situation awareness. It's also one of those when we say keep the human in the loop, we also want the human aware of the state of the system or process at all times. So we don't typically want them to be coming to this this system in an event context where it's not it's kind of novel to them, or it's fresh in their mind. They haven't, or fresh to them, they haven't experienced it recently. And then we want to manually operate if human reliability exceeds machine reliability, or if it's an incident like this where it's a critical task that we want to keep in human hands. Then we apply the knowledge. So it ends up informing design pretty heavily. The type of control and information automation will drive what type of control system you use, staffing levels, different informational requirements, visualizations maybe, or dashboards, your procedures, and your alarms. Information from function allocation can serve as an input to concepts of operation. That's kind of a specific trade term in certain disciplines. You'll hear that a lot in nuclear and certain industrial spaces, less so in other domains, but the concept is still present in other domains if it's not called that. So high level functions are explored first, but detailed functions will emerge as the plant design and INC are finalized. All right, and we're going to wrap up there. So next time we'll get in more to the human system interface design and some of the other characteristics there that we didn't get to this time.